This is a revision video for AQA GCSE Combined Science Chemistry Paper 1. It covers all the key information, but not in a huge amount of detail because otherwise it would be about 40 hours long. The idea is that you can use this video to give you an overview of everything on the paper and also that you can use it as a last-minute cram right before the exam. So the first part of the GCSE is all about elements, compounds and mixtures. And to understand that, you need to understand a little bit about atoms. All substances are made of atoms, and an atom is the smallest part of an element that can exist and still be that element. There are about 100 different elements, and they are shown in the periodic table. Compounds are formed when those elements combine together in chemical reactions. Compounds contain two or more elements chemically combined in fixed proportions. Now, chemically combined is just your exam board's way of saying bonded, and in fixed proportions means that you're always going to have the same ratio of those elements, and that's what a formula tells us. Now, you do need to be able to name those compounds from their formulae. So there are two rules that you need to know. Say you've got two elements in a compound, and if we're talking about ionic compounds, we're going to have a metal and a non-metal. Firstly, you take the name of the metal and you just leave it as it is. Then you take the first syllable of the name of the non-metal. So say it's oxygen, you take ox. If it's chlorine, you take chlor. If it's fluorine, you take fluor. And you then put "ide" on the end of this. So to give you some examples, if we have iron and oxygen, we take the name of the metal, that's iron. We take the first syllable of oxygen, ox, and we put "ide" on the end. Iron, ox, ide. Copper, first syllable of chlorine is chlor. Put "ide" on the end, copper chloride. Now the second rule is for if you have three elements and one of them is oxygen. So you start off exactly the same, you add the first syllable of the non-metal, and then you put "ate" on the end to signify that there's oxygen involved. So if we've got copper, sulfur and oxygen, we've now got copper, sulf-ate. If we've got silver, nitrogen and oxygen, we've got silver, nitrate. And if we've got aluminium, phosphorus and oxygen, we've got aluminium phosphate. Now the next bit of the GCSE is about separating mixtures. So firstly, we should probably define a mixture. So a mixture is two or more elements or compounds that are not chemically combined together. They're not bonded. So for instance, this little picture here has got some nitrogen. You can see it there with its triple covalent bond. It's got some hydrogen and it's also got some ammonia, some NH3. Now they can be separated from each other by physical processes. So what we mean by a physical process is something like heating or cooling or filtering, where we're physically moving the molecules around, but there aren't any chemical reactions happening. So we're not changing the chemicals we've got. At the end of this separation process, I'm still going to have nitrogen and hydrogen and ammonia. They're just going to have been split up from each other. Now there are 5 physical separation processes that you need to know about. Some of them come back a little bit later in the GCSE in slightly more detail, but just to run through them here, we start off and we've got filtration, and I'm going to use filtration if I've got an insoluble solid, so that's a solid that won't dissolve, say sand would be a classic example, and it's mixed up with a liquid, and I want to separate that insoluble solid from the liquid. So I've got a funnel, I've got some filter paper, and I'm going to put the mixture through that. And my insoluble solid is going to stay on the filter paper. We call that the residue. And the liquid is going to go through the filter paper, and we call that the filtrate. My next method of separation is crystallization. So this is a way of separating a soluble solid from a liquid. So this is how you would get salt back out of salty water, for instance, or how you would make crystals of something like copper sulfate, which is this lovely blue colour. So the only piece of equipment I need is an evaporating basin, and then I need some kind of heat source. So that could be using a Bunsen burner, it could be using a water bath. You might have even done this just by leaving it on the side in the sunshine. And the liquid is going to evaporate off and it's going to leave us the solid behind. So if you have a method question which asks you to describe how you would obtain a pure dry sample of a salt, this is the technique you want to be talking about. Oh, I'd make my copper sulfate and then I'd put it in an evaporating basin and I would use a heat source to remove all the liquid, so I would just be left with my dry salt at the end of it. Then we've got simple distillation and fractional distillation, where we're going to use heating and cooling to separate mixtures of liquid. And finally, we've got chromatography, which is also going to separate out some liquids, but this is going to be so that we can analyse them rather than so we can use them afterwards. Okay, so fractional distillation is going to come back in more detail in paper 2 when you're looking at your organic chemistry, but we can talk about it quickly now. The only difference between fractional distillation and simple distillation is that instead of just getting the one sample that I'm trying to get out, I can have a whole range of different liquids that are all mixed together and I can get all of them. So you might recognise this picture as a fractionating column that we would use to extract the different fractions from crude oil, and it's going to separate liquids according to their boiling point, so according to the temperature where they turn from a liquid into a gas. My mixture of liquids will come in at the bottom and it's going to be heated at the bottom. And my fractionating column is going to develop a temperature gradient. So all that means is that it's very, very hot at the bottom and it's much cooler at the top because it's further away from my heat source. Everything is going to evaporate at the bottom, and then as things move up the column and it gets cooler and cooler, they're going to turn back into liquids. And they're going to turn back into liquids at different temperatures depending on what their boiling point is. So in the example of crude oil, natural gas is just going to come out the top of the fractionating column. It's never going to turn back into a liquid because it doesn't get cool enough, whereas things like petrol and diesel and naphtha are going to condense at different points down my column and they're going to be able to be separated like that. Our final separation technique is chromatography. So you've probably done paper chromatography yourself, and so you've done a little setup like this. So you have a stationary phase, which in this instance is a piece of chromatography paper, and you have a mobile phase, which is your solvent, which is usually water if you're doing this in class. So you're going to have a pencil line. You always draw it in pencil because pencil doesn't run. And on that pencil line, you're going to put the sample that you're interested in analysing, and you're going to put some things you want to compare it to. So in this example from the exam board, we've got 5 standards labelled A, B, C, D, E. And you're going to put that chromatography paper into your solvent, and the solvent will rise up the paper, and it's going to take the different colours or different dyes with it. And based on their solubility, it's going to release them at different points. And then you're going to do a comparison. So you're going to look at your sample and look at these standards A, B, C, D, E and see, well, which ones match up? Have I got the same colour that I have in sample A? Then we move on to the structure of the atom. So you need to be able to label the different parts of an atom. You need to know that the protons are the positive particles that are in the nucleus in the centre. The neutrons are the neutral particles, so the ones with a charge of 0, also in the centre. And the electrons are these very, very small negative particles travelling around the outside in the shells. Now, there are a couple of other things you need to be aware of. One is that you are supposed to know the general size of an atom. So on average, it's about 0.1 nanometres. And you also need to know that despite how we usually draw them, i.e. with a really big nucleus so you can see it, the nucleus is actually only 1/10,000th of the diameter of the atom. So that's not going to be an issue for you drawing it. It's fine if you were going to draw an atom to draw the nucleus really big, but just be aware of that for answering questions. Also, one mistake I see students making a lot is that they will write that the relative mass of the electron is 0. Now, that is not true. You don't need to know exactly how big it is. It's about 1/1840, but you do need to know that it has a mass. It does not have a mass of 0. It has a mass of very, very small. You will also need to be able to look at a periodic table square and calculate the number of protons, electrons and neutrons. And if that's something you're still having trouble with, I've got a whole video about that, so you might want to go watch that. Now, when we start looking at atoms in a little bit more detail, what we find out is that there isn't just one version of the atom of a particular element. So say if I look at the periodic table square of carbon, it says that carbon has a mass of 12 and that it has an atomic proton number of 6. And that would tell me that that atom has 6 protons, 6 electrons, 6 neutrons. Now, that is true for the vast, vast majority of carbon, but it is not true for all carbon. The thing that defines carbon, the thing that makes carbon carbon, is that it has 6 protons, not that it has 6 neutrons. So there is a very small amount of carbon in the world that has 7 neutrons. And actually, there's a very small amount of carbon in the world that has 8 neutrons. And we call those different versions of the atom isotopes. So isotopes are atoms of the same element that have different numbers of neutrons, but they do have the same number of protons. You're hopefully already aware that those isotopes exist, and you've probably noticed before that chlorine on your periodic table has a mass of 35.5. And the reason for that is because actually chlorine has two stable isotopes. The periodic table, we just forget about the carbon 13 and the carbon 14 and we say it's got a mass of 12. For chlorine, because there is quite a lot of chlorine 37 and quite a lot of chlorine 35, we have to take into account both of those isotopes, so we report them both. But you do need to be able to take some information from the exam board and work out what the accurate relative atomic mass of a bunch of different isotopes is. This looks really scary, but it's really, really not. So, say for example, the exam question says to me, oh, you've got a sample and it has 90% carbon 12 and 10% carbon 13. What is the mass of that carbon? All you need to do is work out what's 90% of 12, what's 10% of 13. Hopefully, you know that to work out 90% of 12, you can just do 0.9 times 12, and to work out 10% of 13, you can do 0.1 times 13. If you add those together, you can work out that the relative atomic mass of that sample of carbon is 12.1. So the next part of the GCSE gives you an opportunity to look at how, over time, as we gain more evidence, we can change a scientific model. And we use the atomic model to talk through this. Now, this is content that can come up in your GCSE Chemistry and also your GCSE Physics, so it is well worth your time to really make sure that you know it. So we start off with something that you might have heard called the Dalton model, but basically it's this idea that these atoms are indivisible spheres. They're just like little hard billiard balls, like snooker balls. And this first picture, it's an element because the snooker balls, they're all the same colour, they're all the same size, they are the same as each other. So that's what we call the Dalton model. Along comes J.J. Thomson, and he finds that actually these billiard balls, they're not indivisible, they're not unseparatable into little bits. They have something called electrons, they have these little bits of negative charge, and he doesn't know where they are. So he develops this thing called the plum pudding model, and you might just about be able to see they've got little dots on them, they look a little bit like a dice. So he had this idea, a plum pudding is kind of like a Christmas pudding, it's just a big ball of positive charge, and then studded in that are these electrons, and that was his model. Then along comes Ernest Rutherford and his students, and they did an experiment called the alpha scattering experiment. So you hopefully know from your GCSE Physics that an alpha particle, it's one of the types of radioactive decay, 2 protons, 2 neutrons. And what they were doing was they were firing this at this very thin sheet of gold foil. And what they were expecting is that these alpha particles would just kind of push their way through the sheet and it would be the same all over. What they actually found was that a very, very small number of these alpha particles were being bounced straight back the way they'd come. They'd hit a small, dense thing. And what they realised was that actually most of the atom was empty space, and there was this tiny bit in the middle called the nucleus. So then we have a model where we've got this tiny, dense, positive nucleus and all these electrons around the side. Now you're probably looking at that third picture and going, wait, there's way too many electrons in that first shell. Well, yes, there is. And that's what Niels Bohr came up with. So he had this idea that electrons were going to fly in shells, they were going to have distinct spaces that they could be in, and that they would be at different distances from the nucleus, and so that's where we get our shells from. A little bit after that, people started to realise that actually it wasn't just one solid mass in the middle of the atom in the nucleus, and that protons were a thing. So then we start breaking up this central nucleus into protons. And then finally, 1932, along comes James Chadwick, and he realises that there are these neutral masses in the centre of the nucleus along with the protons. So finally, we have protons and neutrons in the nucleus. And now we've got something that looks a bit more like the model of an atom that you've been taught today. So next we move on to the periodic table. You need to know a little bit about how it's arranged, and also how it used to be arranged and how we've kind of moved on from that, and also a few different groups within it. So first up, we need to know that the elements today are arranged in order of their atomic number. So that's the number of protons that they've got. And the reason it's got this slightly funny shape is to make sure that the elements that have the same properties are in columns together, and the columns are known as groups. So if I look at lithium, sodium, potassium, rubidium, cesium, francium, they have very similar chemical properties. They react in the same way with oxygen, they react in the same way with water. The reason that the periodic table is called the periodic table is because the same properties occur periodically. That means at regular intervals. So if you look at the first couple of rows, we have 8 different types of element, and then when you get to the 9th element, we go back to the first type. Now, the reason that all of the elements in group 1 have the same chemical properties, they all behave in the same way and react in the same way, is because they have the same number of electrons in their outer shell. So if you're in group 1, you have 1 electron in your outer shell. If you're in group 3, you have 3 electrons in your outer shell. And that is what is going to determine how you react with other elements. The periodic table hasn't always been laid out like this. So when it was originally devised, we didn't know about protons and neutrons and electrons. So we couldn't say, oh, we'll just put all of the elements that have 1 electron in their outer shell in group 1. So initially, the elements were arranged according to their atomic weight. And that led to a few problems, because although the weight does go up as the atomic number goes up, there are a few little exceptions to this. So for instance, if you arranged things based on their atomic weight, then you would put potassium and argon the other way round. And you'd have potassium, which is a really reactive metal, in the middle of the noble gases, and argon, which is, a noble gas, it's super unreactive, in the middle of this highly reactive group of metals, and that's clearly not right. Also, there were some things missing. So there were some elements that, when the periodic table was formed, the chemists at the time, they didn't know that they existed. Now, you've hopefully heard of Dmitry Mendeleev, very famous Russian chemist, and what he did was say, I'm going to leave some gaps because maybe there are things we don't know yet. And he left these gaps, but also he made predictions about the elements that would be discovered and fill those gaps. And lo and behold, he turned out to be correct. So then we move on to splitting the periodic table up into different categories of elements and saying the characteristics of this category are that they do these things, and the characteristics of this category is that they do these things. So the first two categories that we can split the periodic table into are the metals and the non-metals. You can draw this little staircase, and the general rule is that anything on the left of it is a metal, and anything on the right of it is a non-metal. And you really shouldn't struggle with remembering that, because if you're panicking in an exam, there are some metals that you know what they are, right? You're not going to forget that iron is a metal, you're not going to forget that gold is a metal, and you're not going to forget that oxygen is a non-metal. So just look at where those elements you're really familiar with are, and you'll remember really easily which side is which. Now, metals are defined as elements that will react to form positive ions, and non-metals are the elements that will react and won't form positive ions. You can see just looking at this that the vast majority of the elements are metals. Now, you do need to be able to give just some examples of some properties of metals, so describing words that we can use that are true for these metals. So we've said they form positive ions. We can also say that they are malleable. That means that they can be hammered into shape because those ions can slide over each other. They are conductive, they conduct heat and electricity, and that's because of their delocalized electrons. And also, generally speaking, they have high melting points because of the strong metallic bonding in them. So the only example of a metal that isn't a solid at room temperature is mercury. So next we move on to looking at 3 particular groups within the periodic table. Group 1, Group 7 and Group 0. So Group 1, everybody's favourite, the alkali metals. These are the really, really reactive ones that are very cool when you put them in water. Now, you've almost certainly seen lithium and sodium and potassium being put in water, and you hopefully remember that as you go down the group, they get more exciting, more impressive. And you see them floating on the top of the water because they're really not very dense. They're less dense than water, that's why they float. And you'll have seen bubbles of hydrogen gas being produced. And you'll hopefully even have seen that when you do this with potassium, it produces a lilac flame because the hydrogen ignites on its own, and when potassium burns, it burns with a lilac flame. You might also have seen that when you do this, if you've got some universal indicator in the water goes blue. And the reason for that is the reason they're called the alkali metals. When they react with water, they produce a product, a metal hydroxide, and that metal hydroxide is an alkali. So the metal itself is not an alkali, but it reacts to make an alkali. You'll probably also have seen, if you saw this live, that those 3 metals are usually kept under oil to stop them from reacting with oxygen. So if you cut a piece of sodium or a piece of potassium in half, inside it's really, really shiny, but very quickly it goes almost black because it reacts with oxygen and makes this dark oxide. The next group that you need to be able to talk about are Group 7, which are called the halogens. And because they're in Group 7, they all have 7 electrons in their outer shell. And they consist of molecules made of pairs of atoms. So in the second part of the course, you'll have drawn chlorine. But if you need to draw any of them, if you're drawing fluorine or iodine, you do exactly the same thing. You have 7 electrons in the outer shell, so they share 1 and then have 6 around the outside. But we'll get onto that. Now, I sometimes like to think of Group 7 as being like the opposite of group 1. So group 1 gets more reactive as you go down the group. Group 7 gets more reactive as you go up the group. Because the halogens at the top of the group are more reactive than the ones at the bottom, they can displace them. So if I've got a compound, say I've got sodium chloride, and I add some fluorine, fluorine is higher up the group than chlorine, so it can displace it, can kick it out and take its place in the compound. Finally, we have group 0, which you may know as the noble gases. So this is helium and neon and argon and xenon and all the rest of them. The elements in group 0 have got a full outer shell, and that makes them really, really stable, because the point of chemical reactions is to try to get yourself a full outer shell, and if you've already got one, then you don't need to be involved in any chemical reactions. You need to know that the boiling points of the noble gases increase as you go down the group. So the way I like to think about this is the reason that your boiling point increases is because you have stronger forces between the atoms that need to be overcome. So this is kind of bad chemistry, but I like to think of it a little bit like gravity. So a bigger planet has got stronger gravity, it's going to pull things towards it a bit harder. So if you take argon, that's your third noble gas going down the group, it has bigger atoms than helium right at the top. And that means that the forces between those argon atoms are stronger than the forces between the little tiny helium atoms. And that means that it's going to take more energy for you to overcome it. So you have to heat it up more to get it to a gas. And that's why it has a higher boiling point.
The next unit in the first chemistry paper is all about chemical bonds, metallic bonds, ionic bonds, and covalent bonds. Often a question isn't going to tell you this is a question about ionic bonding, so it's really important that you know when each of these bond types will occur. It's all to do with whether the atoms that are doing the bonding are metals or non-metals, whether they're from the left-hand side of the periodic table or the right-hand side. So, metallic bonds obviously exist in samples of metals. A compound that contains at least one metal and one non-metal will contain ionic bonds, and then a substance made of only non-metals, whether that's a compound or an element, will contain covalent bonds. First up, let's look at this metallic bonding. So, if you look at a metal, what you're going to see is regular rows of positive ions that can slide over each other. And that's why metals are malleable, why they can be hammered into a new shape, because those ions can slide right over each other. They're surrounded by a sea of delocalised electrons. Delocalised just means that they're not attached to one atom, so they're free to go wherever they want, and they can carry charge and they can carry energy, and that's why metals are such good conductors of electricity and of heat. Now the electrons are obviously negative, and those positive ions, they're oppositely charged, so they're held together by a strong electrostatic force of attraction. And that means that, with the exception of mercury, metals are solids at room temperature because they're held together by this really, really strong force, and that would take a lot of energy to overcome it. What you have to remember is that the state something's in at room temperature is all down to whether it's above or below its boiling point and its melting point. And to make it change state, we have to give it more energy. So if room temperature is enough energy to push something over its melting point, then it'll be a liquid. And if room temperature is enough energy to go past something's boiling point, then it will be a gas. And the amount of energy that a substance needs, well, that's down to the strength of the forces holding it together. So because that metal has such strong forces between it, it's going to be a solid. Now you also need to know about substances called alloys. Those are mixtures of metals, or sometimes one metal mixed with some carbon. Now the important thing about that mixture is that the positive ions in that mixture, or the atoms if it's carbon, they're different sizes to each other. So instead of having these lovely regular rows of positive ions, the whole shape gets distorted and the layers can't slide over each other anymore, and that makes alloys much harder. That's why you have alloy hubcaps on a car, because they're much, much harder, so they're much less likely to get damaged. It's also why lots of jewellery is made out of alloys rather than pure metals. If you have pure 24 karat gold, it's actually quite soft and it's very easily damaged. Whereas if you have 9 karat gold, the majority of that is actually made up of other metals, and so it makes it harder and makes it more hard wearing. Our second type of bonding is ionic bonding, and remember, this is going to happen between a metal and a non-metal. And it's all to do with the transfer of electrons, the giving and receiving of electrons. Now you need to remember that the electrons are going to move left to right across the periodic table, just like you read, left to right. So they're going to go from a metal to a non-metal. Now all bonding is to do with elements becoming more stable, more energetically stable. And elements are at their most stable when they have a full outer shell. So for metals, which usually only have 1 or 2 electrons in their outer shell, energetically the best thing to do is to give those electrons away. Whereas for non-metals, which are kind of missing an electron or 2, the best thing for them to do is to take those electrons on. Now in the atom, before this bonding starts, there are equal numbers of protons and electrons, positive and negative charges. So as soon as you start moving electrons around, those charges aren't going to be balanced anymore. So if we take this sodium here, to start with, in the atom it has 11 protons and 11 electrons. So when it loses 1 electron, 1 negative electron, it still has 11 positive charges in its nucleus. But now it only has 10 negative charges to balance those out. And so overall it has a single positive charge. On the other hand, this chlorine atom, when it gains an electron, it's still only got 17 protons, but now it's got 18 electrons, so one of those electrons is not balanced out, and that's why the chloride ion has a single negative charge. You need to be careful when describing ionic bonding about how many atoms of each kind it's going to take to balance out. So say instead of having a sodium atom, I had a magnesium atom, and it needed to lose 2 electrons. It couldn't give both of them to this one chlorine atom, because chlorine can only take 1 electron, it only has 1 space in its outer shell. So I would need 2 chlorine atoms to balance out that single magnesium atom. Now once this transfer of electrons has taken place, and I have a positive ion and a negative ion, those are going to join together to form a giant ionic lattice. It's giant because this is never going to happen with just a couple of atoms, right? This is going to happen with thousands and thousands of atoms at the same time, and they're going to make this huge lattice. The giant ionic lattice is held together by a strong electrostatic force of attraction, and it's acting in all directions. My lattice here is only drawn in 2 dimensions, but remember this is going to be a 3D structure. So that positive ion is going to feel a force going up and down and forwards and backwards and left and right. It's a really, really strong force. So again, ionic substances are solids at room temperature, because room temperature doesn't provide them with enough energy to surpass their melting point. Because this giant ionic lattice is made up of charged particles, these positive and negative ions, it can conduct electricity. But in order to conduct electricity, the ions need to be free to move, otherwise they can't carry the charge anywhere. So when it's a solid, the ionic compound is not going to conduct electricity. But as soon as we melt it by giving it energy, or dissolve it in water so that it's aqueous, then it will be able to conduct electricity. Our third type of bonding is the covalent bonding, and this will occur between pairs of non-metal atoms when they share 1 or more pairs of electrons. It's always pairs. If you've drawn 1 electron on its own in a covalent bond, then something has gone terribly, terribly wrong and you need to look again. Now, there are 2 types of covalent substances. There are small covalent molecules, which you might have seen referred to as simple covalent molecules if you've got an older revision guide, and there are giant covalent structures, which you might have seen referred to as macromolecules. There are 8 small covalent molecules that you need to be able to draw. 7 of these were in the old GCSE, but nitrogen is new, so I would pay particularly close attention to that in case you have an old revision guide that doesn't include it. In all of these small covalent substances, what you're going to see is in the covalent bond there is a pair of electrons, and we draw that with a dot and a cross to show that 1 electron has come from one atom and 1 electron has come from the other. In all cases, all of the atoms are going to have a full outer shell. So for hydrogen, that means it's going to have 2 electrons in total, and then for every other type of atom, it's going to have 8. The ones to watch out for are oxygen, which has a double bond, and nitrogen, which has a triple covalent bond, which is what makes nitrogen super unreactive. Small covalent molecules, like oxygen or nitrogen or methane, tend to be gases or liquids at room temperature. Now the reason for that is that holding those molecules together isn't a bond, isn't something really, really strong, it's just something called a weak intermolecular force. And it's really easy to overcome that weak intermolecular force because it doesn't take very much energy. The bigger a molecule is, the stronger the weak intermolecular forces between it will be. That means that as small covalent molecules get bigger and bigger, they do start to become solid. So for instance, if you think about a polymer, that's got thousands and thousands of atoms. So actually the weak intermolecular force can become quite strong. But you need to be really, really clear that it is not the covalent bonds that break when these become liquids and gases. These small covalent molecules can't conduct electricity because they haven't got any charged particles. There aren't any delocalized electrons and there aren't any ions. We just mentioned polymers. Polymers are very long chains of repeating units, and we call those repeating units monomers. Those monomers are held together by strong covalent bonds between them to form a really long chain. But between one really long chain and the next very long chain, there's going to be a weak intermolecular force. Because the polymer chains are so long, the weak intermolecular forces actually get quite big. They're still nowhere near the size of an ionic bond or a covalent bond, but they're enough to make many polymers solids at room temperature. Finally, you need to know about giant covalent structures, and there are a few different examples that you need to be familiar with. So these are structures that are made up of usually thousands of atoms held together by strong covalent bonds. It's not like our small covalent molecule where we've got maybe 3 or 4 atoms bonded together and then just a weak intermolecular force between them and the next 3 or 4. These are all bonded together. So your first example is diamond, and diamond is one version of carbon, one form that carbon can take on when it bonds. In diamond, every carbon atom makes 4 strong covalent bonds. Now, it's really common for diamond to be compared to graphite in an exam question, and so often we see students write, diamond has 4 strong covalent bonds. No, it doesn't. Diamond has thousands and thousands of strong covalent bonds, but every carbon atom in it makes 4 strong covalent bonds. And it's really worth your while to use that word strong, because often strong is an extra mark over and above just saying a covalent bond. Because it has all those really strong covalent bonds, the atoms in diamond can't slide over each other like the positive ions in a metal, and so that makes diamond incredibly hard. Like our small covalent molecules, it doesn't have any delocalized electrons and it doesn't have any ions, so diamond can't conduct electricity. Now, in contrast to that, graphite is still made of carbon, but in graphite every carbon atom only makes 3 bonds. And that means that it's got 1 electron left over per carbon atom that isn't part of the bonding. So that electron becomes delocalized, it becomes free to move and carry the charge. And that is why graphite can conduct electricity even though it's a non-metal. Now, because graphite's missing that extra set of bonds, because every carbon atom is only making 3 bonds, not 4 bonds, it forms these sheets made up of hexagons, and those sheets aren't bonded together. There's just a weak intermolecular force between them, so they can slide over each other, and that makes graphite really soft and slippery, and so it's really useful as a lubricant, particularly somewhere that you might not want to put oil because it's getting too hot and there's a risk that the oil might set on fire. You also, for the new GCSE, need to know something about graphene. Now, graphene is just a single layer of graphite. It can still conduct electricity, and it's a really exciting material because we might be able to use it in all sorts of things like bendable electronics. Your third and final version of carbon is something called a fullerene. Now, fullerenes are a type of nanoparticle. Those are really small particles with a few hundred atoms, maybe 1 to 100 nanometers across, and they tend to form tubes and balls and other kinds of small particles. You particularly need to know about C60, that's Buckminster fullerene, which is made out of 60 carbon atoms joined together. The other type of giant covalent structure you need to know about, which has nothing to do with carbon, is silicon dioxide, or you sometimes hear it called silica. It has a structure like this, where every silicon atom is joined to 4 oxygen atoms, and every oxygen atom is joined to 2 silica atoms. It basically has exactly the same properties as diamond, so you need to know, because it has all these strong covalent bonds, it has a really high melting point, so it's really useful for things like lining the inside of a furnace. And because it has those strong covalent bonds using up all of the electrons, there aren't any electrons left to be delocalised, so it also can't conduct electricity. The third unit covered by the first chemistry paper of AQA GCSE Combined Science is Quantitative Chemistry, which is basically just using maths to figure out useful things like how much product a reaction should make. To do just about anything in quantitative chemistry, you need to be confident using the relative atomic mass of an atom. This is really clearly labelled on the periodic table, but so often we see students panicking in an exam, picking the wrong number, and then of course none of their calculations work. The relative atomic mass of an atom is the mass of that element compared to 1/12 of the mass of carbon-12. The first part of quantitative chemistry is all about the conservation of mass. Conservation means keeping things the same. So the law of conservation of mass says that no atoms are lost or made during a chemical reaction. That means in a simple equation, you have to have the same number of each element on the left and the right. Take this equation for photosynthesis. There are 6 carbons on the left in the 6 carbon dioxide molecules, and 6 carbons on the right in the glucose molecule. This also means that in terms of mass, the mass of the atoms in a reaction can't change. Now, sometimes it might look as if the mass does change, And if this happens, you can guarantee it's because there's a gas involved. Say I have 6 grams of magnesium and I grind it up to a really fine powder and burn it. At the end of that chemical reaction, I should have 10 grams of magnesium oxide. Now that's not because I've magically created extra atoms. It's because the oxygen, which used to be flying around in the atmosphere and not pressing down on the weighing scales, is now stuck fast to that magnesium. So we're weighing atoms that existed before, but they weren't being weighed. Likewise, if I take 5 grams of calcium carbonate and I heat it up until it thermally decomposes, I'll be left with 2.8 grams of calcium oxide, because some of the atoms in that calcium carbonate have been released into the atmosphere and they're no longer being weighed. They still exist, they're just not in my little pot on the weighing scales anymore. The first real calculation that you're going to do as part of quantitative chemistry is relative formula mass, shown by the symbol MR. You have to be able to do this to do almost anything else in quantitative chemistry. All you're doing is taking the relative atomic masses from the periodic table and adding them up. So for sodium oxide, there are 2 sodiums, so 2 times 23, and 1 oxygen, so 1 times 16. Add it all up and you get 62. If you need a little bit more practice doing that, I have got a whole video of practice calculations. Now for higher tier only, you need to be happy using something called a mole. A mole is just a really big number. You know that a dozen means 12, and a million means 1 with 6 zeros after it. Well, a mole is 6.02 times 10 to the 23, and we sometimes call that number Avogadro's number or Avogadro's constant. It represents the number of atoms in the relative atomic mass of a substance in grams. So say the number of atoms in 12 grams of carbon, or 16 grams of oxygen, or 1 gram of hydrogen. That's also the same as the number of molecules in 44 grams of carbon dioxide, or 18 grams of water. Once you know what the relative formula mass of a substance is, you can start saying, well, how much does 5 moles of it weigh? Or you can start saying, well, if I've got 220 moles of carbon dioxide, then how many moles is that? Again, if you're not super confident about that, I have got another video with a few practice calculations. Imagine you're buying apples and the price is £3 per dozen. You have £18. How many can you buy? Well, you'd do £18 divided by £3 and you'd get 6 dozen. Exactly the same idea here. You can also work in the other direction. Say I want to know how much 4 dozen apples would cost me. Well, 4 times £3 is 12. Now, once you're happy with both MR and moles, you can start doing something useful. Say I've got 7 tonnes of copper ore and I want to know how much copper I can extract. I need to use the relative masses of the substances involved and the balanced symbol equation to work out something called the predicted yield or the expected yield. So let's take one example. I've got 510 grams of aluminium oxide, and I want to know how much aluminium I can make from that. The first thing I need to do is work out how many moles of aluminium oxide I've got. And in order to do that, I need the MR, the relative formula mass. So just like we said, we're just going to add up the masses of all the atoms in that compound. We've got 2 aluminium atoms, each with a mass of 27. We've got 3 oxygen atoms, each with a mass of 16. So I add together 2 times 27 plus 3 times 16, and I get 102. So now I know that 1 mole of aluminium oxide would weigh 102 grams. But I don't have 102 grams, I have 510. So I do 510 divided by 102, and that tells me I've actually started with 5 moles. Now I need to go back to my symbol equation. What my symbol equation actually tells me is the ratio of the different chemicals that are taking part in this reaction or being formed. So you can see that aluminium oxide doesn't have a coefficient, it doesn't have a big number in front of it, but aluminium has a 2. So what that tells me is however many moles of aluminium oxide I started with, I'm going to make twice as many moles of aluminium. So if I started with 5 moles of aluminium oxide, I must be going to make 10 moles of aluminium. Now I just need to know what the relative mass of aluminium is. So I go back to my periodic table, I see that it's 27, and then 10 moles times 27 grams per mole weighs 270 grams. The next calculation for quantitative chemistry is concentration. If we leave the numbers out for a second, concentration is just a measure of how many dissolved particles are in a set volume of solution. So we call those dissolved particles the solute, and we call the liquid that they're dissolved in the solvent. Now our units for concentration are grams per decimetre cubed. A decimetre cubed is exactly the same thing as a litre, and it contains 1,000 centimetres cubed. And quite often you might get a sneaky question where they give you the volume in centimetres cubed and expect you not to notice, so make sure you keep an eye out for that one. Now if you know that the units are grams per decimetre cubed with that slash there in the middle, Well, hopefully you know from maths that slash is really a divide sign. So what we've got is grams divided by decimetre cubed. Well, grams is a measure of mass and decimetre cubed is a measure of volume, so we're doing mass divided by volume. You've almost certainly encountered the idea of limiting factors in biology where you studied photosynthesis. That idea that the limiting factor is whatever is slowing photosynthesis down. So it could be that there's not enough carbon dioxide, or it could be that there's not enough light, or it could be that the temperature is too high or too low. In chemistry, we have a very similar idea, limiting reactants. So this is the idea that if I've got two chemicals reacting together, one of them is going to be in excess, there's going to be too much of it, and one of them will be the limiting reactant, the one that there's not enough of. This reactant is going to be completely used up in the reaction. So imagine I've got a really big beaker full of acid and I put a tiny piece of magnesium in it. The magnesium is going to react completely and disappear, and that means that that one is the limiting reactant. The fourth unit you need to know about is chemical changes. This starts with reactivity, looking at how metals react with oxygen, with water, with acid, and then using those reactions to place them in an order of reactivity. You need to know that metals react with oxygen to form compounds called metal oxides. So this could be a simple question where you have to complete a word equation, like saying tin plus oxygen, what does it make? Oh, tin oxide. Metals react with water to form metal hydroxides and hydrogen. So similar thing, lithium plus water goes to lithium hydroxide and hydrogen. You should know that those metal hydroxides are alkalis, so they'll turn universal indicator blue, and you should know your gas test for hydrogen, which is that if you ignite it, it burns with a squeaky pop sound. Now, very few metals are reactive enough to react with water in a way that you can see clearly, so really you're thinking about your alkali metals, maybe calcium, magnesium if it's hot enough water. So if you were trying to compare the reactivity of some metals, if I put potassium in water, there's a lot of bubbles that I can see, whereas if I put copper in water, I won't see any reaction at all. So I could look at those and I could say potassium is more reactive because it produces more bubbles. Next, you need to know that metals react with acids to form a salt, which is an ionic compound, and hydrogen. So again, you can test for that hydrogen using your squeaky pop test, and you can judge the reactivity of those metals on how quickly it reacts with the acid, how many bubbles you see. You do need to be able to name those salts. So there are 3 acids that you should know about for GCSE: hydrochloric acid, sulfuric acid, and nitric acid. The salts that are formed are each going to have 2 names, kind of like a first name and a surname. So if you put a metal in hydrochloric acid, the name of the salt will be the name of the metal followed by chloride. So for instance, iron and hydrochloric acid will make iron chloride, or tin and hydrochloric acid would make tin chloride. Sulfuric acid makes sulfates, so magnesium sulfate, zinc sulfate. Nitric acid makes nitrates. You need to know that metal oxides can react with those same acids to form salts and water, because the oxygen from the metal oxide is joining up with the hydrogen that you had when you were just putting some metal in to make water. Metal carbonates react with those same acids to form salts, water, and carbon dioxide. And you should be able to write word equations and symbol equations for all of those reactions. Remember, to test for carbon dioxide, you need to bubble it through lime water, and the lime water will go milky or cloudy, it turns white. You can use all of these reactions to help place metals in order of reactivity. Your specification just mentions potassium, sodium, lithium, calcium, magnesium, zinc, iron, and copper, which is slightly fewer metals than we used to talk about in the old specification. Remember to talk about what observations you're making, so what can you actually see? It's not enough to say, I think that magnesium is more reactive than iron because I saw it react faster. You didn't see it react, what you saw were maybe the bubbles of gas being given off. Make sure that in that reactivity series you know where carbon and hydrogen go. So for instance, you know that the only thing on that list that's less reactive than hydrogen is copper. So if you put copper in acid, you're not likely to see a reaction because it's not going to be able to displace the hydrogen. Metals are defined as elements that make positive ions. So the reactivity of a metal is related to how easily it makes those ions. If you have an element from group 1 that only needs to lose a single electron to become a positive ion, that's very, very easy to do, and that's what makes the group 1 metals so reactive. Also, the further you go down a group, the easier it is for it to lose that outer shell electron, and therefore the further down the group you go, the more reactive the metals get. Now we can use this information about metal reactivity to think about how metals can be extracted. So very unreactive metals like gold, silver, platinum, copper, things that you would make jewellery out of, they are just found as elements in the Earth's crust. We sometimes say they're found native. Slightly more reactive metals, like iron and tin and lead, can be extracted by reduction with carbon. That basically means if you've got some iron oxide and you heat it up with carbon, because the carbon is more reactive, it displaces the iron. It steals away that oxygen impurity, and so what you're left with is carbon dioxide and pure iron. If you're sitting the higher tier, then you need to be able to say, in terms of electrons, whether a reaction is an oxidation reaction or a reduction reaction. The way to remember this is OILRIG, which stands for oxidation is loss of electrons, reduction is gain of electrons. So if we take the reaction of magnesium with hydrochloric acid to make magnesium chloride and hydrogen, if we just look at the magnesium, on the left-hand side, it's a magnesium atom. It has the same number of electrons as protons, 12 of each. On the right-hand side, when it's made a compound, it's formed magnesium ions, 2+ ions, and that tells us it has 2 more protons than electrons. On the left, it has 12 electrons. On the right, it only has 10. It's lost 2 electrons, so we say that it has been oxidised. The hydrogen, on the other hand, started off as hydrogen ions, which have no electrons but 1 proton. That's why they have a single positive charge. On the right-hand side, they've now regained that electron. Reduction is gain of electrons, so the hydrogen has been reduced. You also need to know about neutralisation reactions, reactions where the pH of a solution moves closer to 7. These reactions are going to include an acid, a substance that produces hydrogen ions. The neutralisation could be by an alkali, which contains hydroxide ions. Alkalis are an example of a base. So bases are any chemical that can neutralise an acid, and some of them are soluble, and we call them alkalis, but some of them, like metal oxides, are not soluble, they're insoluble. We can determine how acidic or alkaline something is by using something called the pH scale, a scale that goes from 0 to 14. You need to know a general equation for the neutralisation of an acid by an alkali. This is an equation that works for any acid and any alkali, so we don't include the spectator ions. So we have H+ for the acid, OH- for the alkali, joining together to form water. If you're sitting higher tier, you need to know the difference between strong acids and weak acids. This is different to concentrated and dilute. So strong acids are hydrochloric acid, sulfuric acid, and nitric acid. They are acids that are completely ionised in water. That means as soon as they dissolve, they give up their hydrogen ion. Weak acids, like citric acid, ethanoic acid, and carbonic acid, are only partially ionised. So some of those particles, when they dissolve, will give up a hydrogen ion, but some of them will remain intact. Finally, for Unit 4, you need to know about electrolysis. This is a pretty big subject, and if you're not sure about it, I have got a whole video about electrolysis. Electrolysis means splitting ionic compounds using electricity. It has to be an ionic compound because a covalent compound doesn't have overall charged particles that will be able to move in response to the electricity. The ionic compound is called the electrolyte, and it needs to either be melted or dissolved in order for the ions to be able to move. We call those ions cations and anions. The cation is the positive one and the anion is the negative one. Those ions are going to move in response to charge. The positive cations move to the negative cathode and the negative anions move to the positive anode. This is because opposites attract. When they arrive there, they will be discharged, which means they'll stop being ions and turn back into atoms. This happens by them either gaining or losing electrons. If you're sitting higher tier, you need to be able to write half equations for these discharge processes. So for instance, the cation aluminium has a 3+ charge. Therefore, it needs to gain 3 electrons in order to turn back into an aluminium atom. This is called reduction. Oxide ions are an example of an anion. When they reach the anode, they need to lose their electrons. They're oxidised. Be really careful with these anions. Firstly, they have names that are slightly different from the names of the element. So for instance, you have an oxide ion, even though the element is called oxygen. Also, when these anions are discharged and turn back into elements, they usually go round as pairs. So for instance, oxygen goes round as O2. That means when you write the half equation, you need to remember to write 2 oxide ions, and you also need to remember that 4 electrons will be lost in total. The extraction of aluminium is named as an example of electrolysis, so you need to know that it's extracted from aluminium oxide, which is mixed up with cryolite to help to disrupt the lattice. You should be able to talk about how this is a very expensive process, because it takes a lot of energy to melt the aluminium oxide, it takes a lot of energy to provide the electricity to do the electrolysis, and also because the electrodes, which are made of graphite, will gradually wear away and need replacing over time. You also need to know about the electrolysis of solutions. These solutions will contain the ions from the compound, but also hydrogen ions and hydroxide ions. And the hardest thing to remember is which ions will be discharged. There are 3 rules you need to know. Firstly, the most reactive cation will stay in the solution. That means that the only metals you can extract by electrolysing a solution are your jewellery metals: copper, silver, gold, platinum. If there's any other metal in the solution, then it's more reactive than hydrogen, and instead of the metal being extracted, it will be the hydrogen that's released. Your second rule is that halides are preferentially discharged. So those are ions that have come from group 7. If there are no halide ions in your solution, then the hydroxide ion will be discharged, and that will release oxygen. The 5th and final unit in the first chemistry paper of AQA's GCSE Combined Science is energy transfers. You need to know that energy is conserved in a chemical reaction, which means that overall it stays the same. So over the course of that reaction, the energy can move around and be stored in different places. So it could move from the reactants to the surroundings and warm them up, or it could be taken in from the surroundings and you could end up with products that had more energy in them than the reactants you started with. But overall, it has to remain the same. We can use temperature changes to tell us whether a reaction is exothermic or endothermic. You almost certainly know that you go out of an exit, and that therm usually refers to heat, so think like a thermometer. So you can think of an exothermic reaction as one that probably gives out heat. Now, it could be other types of energy, it could be light, it could be sound, but in the majority of cases we are talking about heat, and if you get given a quantitative question where it's got some numbers, it's almost certainly going to. There are 3 named examples of exothermic reactions that you need to know: combustion, so burning things; oxidation reactions, that could be, say, burning a metal in oxygen; and neutralisation, so when we mix an acid and an alkali together. In terms of what they're used for, you need to know that they can be used for self-heating cans, the kind of cans that you might take camping with you, or for hand warmers. You can think of endothermic reactions as being like the opposite of an exothermic reaction because they take in energy from the surroundings. So generally speaking, they're going to make the surroundings cooler. Your specification mentions thermal decomposition, so that could be something like heating copper carbonate with a Bunsen burner so that it breaks down into copper oxide and carbon dioxide. Reaction of citric acid and sodium hydrogen carbonate. And also, it's not explicitly measured in your spec, but it's probably worth knowing that photosynthesis is another example of an endothermic reaction, because of course it takes in energy in the form of sunlight. Endothermic reactions can be used for those cooling packs that you might use instead of an ice pack. There is a required practical in this unit, and it involves investigating the variables that affect the temperature changes in reacting solutions. So there isn't one specific named example here, there are lots and lots of different experiments that you might have done in your class, and the exam board can just give you some information about a new situation you haven't met before. So they could ask you to write a method, they could ask you to interpret some data. So if you're asked to write a method, there isn't a specific technique that you need to know about, but you need to talk about things like the fact that you're probably going to do this reaction in a polystyrene cup or some kind of insulated vessel to try and stop heat changes. You're probably going to want to use a digital thermometer because that's likely to have a higher degree of precision than a thermometer that you just read yourself, because it can probably go to a couple of decimal places, whereas if you're just reading it by eye, you're not really going to be able to be more accurate than half a degree C. And you're going to want to mention control variables, so things like if you were going to measure the temperature change when you add some metal to some acid, you would want to keep the volume of the acid the same and the concentration of the acid the same and the size of the piece of metal the same. They could give you some data from an experiment like this and ask you to just say whether it's exothermic or endothermic. So if the temperature on the thermometer goes up, it's exothermic. If the temperature on the thermometer goes down, it's endothermic. You need to be able to discuss reaction profiles, which are these diagrams which show you how much energy the reactants and the products have. Now you'll know from Unit 6 that in order for reactants to react, they have to collide with each other, which means bang into each other, and they need to have a certain amount of energy called the activation energy. So what that means is that for any reaction to start, the particles need a certain amount of energy. In order to get up to this transition state here, they need to acquire some energy from somewhere, and it might be that they can take in that amount of energy from their surroundings, in which case the reaction is going to happen pretty much spontaneously, or it might be that that's quite a lot of energy and you need to heat the reaction to start it off. Whatever that amount of energy is, it's called the activation energy. So if you're labelling one of these reaction profiles, you want to label the activation energy from the height of the reactants up to the height of the transition state. Now, the other thing that you can do with these reaction profiles is tell whether a reaction is exothermic or endothermic. And this is really straightforward once you know what you're looking for, but it can just be slightly counterintuitive the first time you meet it. So, the line on the left represents how much energy is stored in the reactants, how much chemical energy is stored in their bonds. And the line on the right is how much energy is stored in the products. Now you can see in my first example here that the reactants have more energy than the products. Well, we said at the start of this section that energy is always conserved. There must be the same total amount of energy. So if you imagine my reactants have 200 kilojoules of energy and my products only have 100 kilojoules of energy, well, where did the spare 100 go? It was given out, it went out into the surroundings. And so my surroundings would have got warmer, and that makes this an exothermic reaction. So in every exothermic reaction, you're going to see your reactants being higher than your products. If we look at my second example, this is the exact opposite. So this is an endothermic reaction. We start off with our reactants only having, say, 100 kilojoules of energy, and then our products at the end have got 200. Where have they got that extra 100 from? Well, they've taken it in from the environment around them. They've taken it in from the surroundings. So the surroundings will have got cooler because now there's more energy stored in the chemicals. Now, if you're taking higher tier, you also need to be able to do bond enthalpy calculations and work out what the energy change of a reaction is. Now, my number one piece of advice for this would be that when you're doing one of these questions, if they haven't drawn out the reactants for you, draw them yourself. Because the number one mistake that we see is that students do the calculation completely right, but they miscount the number of bonds that are being made or being broken, and so they get the calculation slightly wrong and they come out with completely the wrong answer. Now, the first thing that you need to know is that breaking bonds needs energy. It takes energy in, and making bonds will release energy. Be really, really careful that you're not accidentally saying that the energy is made, because it's not. The energy was already there, it was already in the atoms, but when they bond, it's going to be released. If you're struggling to remember this, I like to think of energy as being a bit like money. So imagine you go to a shop, and if you knock something over and break it, you have to pay for it. You have to give them some money, and they take that money away because you've broken something. So if you break a bond, it takes in the energy. But then if I make something and I take it to the shop for them to sell, they will give me some money for it. So when I make something, I get the energy back. So the exam question is going to give you a symbol equation like this. And what I've done is I've drawn out my molecules. Now, the helpful thing about having drawn that is that I can now see really, really clearly that I have 2 hydrogen-hydrogen bonds, 1 oxygen-oxygen bond, and 4 oxygen-hydrogen bonds. Those bonds all have different bond energies, and they will be given to you in the question. Now, looking at my equation, in order for this reaction to happen, the hydrogen-hydrogen bonds need to break and the oxygen-oxygen bond needs to break. So, when those bonds break, some energy will be taken in. I can use the bond energies that have been given to me in the question. I can see that each one of those 2 hydrogen-hydrogen bonds will require 436 kilojoules per mole to break, and then the oxygen will require 498 kilojoules per mole to break. So if I add all of those up, I can find out that this is going to take me 1,370 kilojoules to do. My next step is going to be to make some bonds. So again, I look at the bond energies that they've given me in the question, and I can see that an oxygen-hydrogen bond has a value of 464. So you can write down 4 times 464, or you can just write down the value of each bond as you colour it green. And if I add those up, I find out that the energy being released is going to be 1,856 kilojoules. Now, the final part of this question is going to be for me to calculate something called the delta H, and that's the overall energy change. So what you want to do is to work left to right across your page, just like you were reading the equation, and you're going to do the energy taken in, take away the energy that's released. So in this example, it's 1,370, take away 1,856, which comes up with minus 486. Now, we saw just a little bit earlier with those reaction profile diagrams that whenever you have an exothermic reaction, energy is lost to the surroundings, there is a negative energy change. So this negative number here tells me that burning hydrogen in oxygen is an exothermic reaction.